going to be as easy. In the last 2 weeks, I mean our full 2 weeks, we've got 2 weeks of class. We have the Tuesday of finals week to review, and then the finals going to be on Thursday. I know it's hard sometimes coming back after Thanksgiving. It takes sometimes a week to get back into things, but if you kind of just bear down these 2 weeks, we've got not a real long unit, but there's a lot of different little small topics here. On the objectives, it's going to feel long. I'm not going to cram anything in just because we're trying to finish anything in 2 weeks. This is the normal time that we have for it, the time that I allow for it. So we're not behind, we're not rushing through anything. But it's just still another full unit. I don't go any lighter just because it's the last 2 weeks. So just prepare to work on homework like normal. And we're going to start talking about fluids and buoyancy today. We'll get into gases, talk about thermodynamics and heat. Some of the things that we do here, if you've had chemistry, might be a little familiar. We'll have a little bit with the ideal gas law. We'll do calorimetry. I might have done that in Chem 1, I think at the end. Maybe a little bit with thermodynamics. So there are topics here that you might have seen or heard of before. That makes some of the things a little bit easier. I don't think this is the hardest unit, but it's not as easy as the last one either. So just going to be prepared to, I think, work a little bit more than you had to that last unit. If you have your objectives, pull those out. Start looking at those right at the beginning. Don't forget your mastery labs are due Thursday. If you have any questions about those, maybe ask me during lab. I've got homework up on mastering physics now. The first one, which will be up through everything we covered today. That'll be due next Tuesday. And then there'll be, I might separate it into 2 separate assignments over the different topics, but there'll be a couple more coming up toward the end. That last week when we get there, the Tuesday of finals week, we'll have class. It'll be a review day. We might be wrapping up a few things from the Unit 6 that we're on, but I won't be covering much new material that day, so there won't be a lot of new things to learn at that point. Usually we're done with the unit by Thursday of next week. The Tuesday, I'll let you know on that Thursday. We usually don't do in-class assignments. We don't do anything for credit that day. It's a review day that's kind of light for those of you who might have finals that day or other days. Sometimes people choose to skip that class if they feel like they don't need the review, but I'll tell you more about that as we get closer to that week. We do have 2 more labs coming up, and this mastery lab will be due this week. Okay. If you look at the objectives here, there's 2 pages on this one also, just like the first unit. There's 19 objectives on here, so that may feel long, but there are a handful in here again where we have things where I ask you for a definition. And you'll see one like number 6 says just translate temperatures from Celsius, Fahrenheit, or Kelvin scales. That's just a simple conversion there. There are some that aren't as long. And also, usually on this last objective, I put all these on here at the beginning because sometimes there's things that I want to cover. But most times I end up crossing off a good 4 or 5 of these that are on here. So it may not feel or may not be as long as it looks here. But either way, as I said, I'm not going to rush through anything just because we only have 2 weeks left. We'll cover what we have time for, which will be a good portion of what we see here on the objectives. And we'll start here talking about pressure. We're going to define a few things first for pressure and density, mainly so that we can start getting into our discussion of fluids. Pressure we're going to define just as a force per area. Okay? This P is a lowercase p, but I'm not going to write it any differently than a normal p. I mean, it's not a lowercase p with a vector, which would have been momentum from before. It's not a big P for power, it's P for pressure. You probably won't mix that up with momentum or power, those kind of things here, but it's a lowercase p if you want to try to write that way in your papers. Okay. This is just force per area, so pressure is not the same thing as force. Sometimes at the beginning people kind of mix those 2 things up because they kind of feel the same, like I'm exerting pressure by pushing on this board right here. pressure is just the force over the area that the force is acting on here. Okay. The force here is the force or the perpendicular component of force for us. I'm writing this in parentheses because that's the way it's defined. This force is the component of force that's perpendicular to the area over which the force is acting. Okay? It really is for us just going to be some force. Okay? Now, when I push on the board here, my hand's going at an angle. We have components here of my force that are parallel to the board and perpendicular. The force component that's perpendicular is the one that's kind of related to the pressure. We're going to relate pressure, though, most times to things like the pressure from the atmosphere on the window of a plane, or the pressure of maybe a fluid in a container. The forces from pressures that we're going to talk about are always going to be perpendicular. So you're not going to have to calculate these components. In general, it's defined that way. This force is assumed to be the perpendicular component of the force, but we don't put perpendicular right here. It's just always assumed to be the perpendicular force. For the kinds of pressures we're going to deal with, like in a fluid, imagine the fluid with all the walls here of the container. The fluid is pushing out, down, out against the walls, all perpendicular to the container that's holding that fluid. So that kind of force here from the fluid, or these pressures here, are always perpendicular to the walls of the container. Okay? Those are the kinds of things we're going to be looking at. So this won't really be a point of emphasis. I'm writing it down because it always needs to be that way. Just know that we're not going to really have to worry about calculating it that way, though. The area is, or the A is just the area, okay, where pressure then is force per area. So we have units of newtons per square meter. That is what we call a Pascal, or a unit of pressure. This PA here is a capital P and a lowercase a, not a P with a subscript of A. We are going to see that later on, with the P with the subscript of A represent the atmospheric pressure. So just be careful when you're writing these. Sometimes people will mix up a P with a subscript with this PA for Pascal. A lot of times when we write down units for pressure, you might just choose to leave it in newtons per square meter, so that maybe you don't mix it up with that, because we're going to have equations with pressures where I could have atmospheric pressure is equal to 5 pascals, and if these look the same, you might get a little mixed up and think, well, these can cancel out or something if you make them look the same. So one way to avoid that would be, this is the same thing as saying PA is equal to 5 newtons per square meter. Again, that notation as a subscript means something. That's just a PA for a Pascal. Okay? So just be careful when you write out those Pascal units there. We also have a conversion factor here for pascals to pounds per square inch. You don't have to memorize this. I'm just writing it down so you have it for reference. You'll find that number in the front cover of your book, like all your conversion factors, and it's one that I'll give you on the exam if you need to do any conversions with it. You've probably seen this unit here much more commonly than you've seen pascals or newtons per square meter. Where have you guys seen pounds per square inch before?
Tires.
Tires, most commonly. Well, PSI, you've seen that before probably. That's a unit you're more familiar with.
Torque.
Torque, you'll see foot-pounds. Yeah. If you're seeing this, then you're not seeing torque. You might think you're seeing torque, but, and it might have been related somewhere with the pressure, but usually it would have been in foot-pounds, just like a newton meter for, yeah. Okay, let's talk about density now. How do you find the mass density of something?
Density is mass over volume.
Density is mass over volume. And what variable do you want to use for density? What What letter? D.
Little d.
Little d. We don't use little d. We use a rho. You saw that in the homework last time. I think we had a steel wire with some density that was given to you. So make sure that this row does not look like that P, because we're going to have rhos and P's in the same equation. Now, if you're wondering why we don't just call it a D, I'm not going to switch. Our book uses this, I'm going to use this, and in general in physics we use that, and in math we use that. A little d in math means a derivative or a differential, and we just can't have d's and densities in the same equation because they end up being the same thing. And I know that doesn't matter to you because you don't speak that language of calculus, we don't use it here, but that's where it comes from not calling it a d. I know we've used a d before for things like distance, and speed is distance over time, but it's just, we call it rho, leave it like that. It may be unfortunate if you can't write a rho, if your rows look like P's, but just get comfortable writing those and don't change it to a D. Leave it like this so that I know what you're going to be using. We use this quite often when we're talking about fluids and buoyancy, and we're going to see it in our pressure equations also. So we'll have densities of fluids or things like that. So this has units, we've seen this before, kilograms per cubic meter. If you look in your book, we have, I'm just putting this here in brackets for the unit, on page 318, you have a table of densities. You'll need to refer to this table when you're doing problems with buoyancy, with pressures, to find densities of some common substances. This is table 9.2. If you have your books, open up to that page just so you can look at it and get familiar with it. You'll see on there, it gives you densities of common substances. It tells you the units in kilograms per cubic meter for all these values, and then you'll see things on here for blood, gasoline, copper, water, anything on here that you might need. A very common one for us to be using, we'll use water quite often, so you'll see down there at the bottom, you've got 1,000 kilograms per cubic meter for your density of water. And then all these other things on here. I'll give you this on the exam. You don't need to memorize any of these numbers. You probably will have fresh water memorized because you'll use it quite a bit, but just know how to use this. This sheet that I have here has a few tables here, a few more here on the back side. There's quite a few constants that we're going to be using throughout this unit. This page, or something like this page, I'll give you on the exam. Okay? So you just need to know it's in your book. We'll have things like specific heat values, densities, latent heats, expansion coefficients, all these different things that you'll need to be able to look up and know when to use these. So for a density, you can calculate it just like that if you need to, but if it's for something like water or something else, we'll just calculate it, or we'll just get it from our table here. I have a few equations on here that sometimes I give you, but once we get closer to the final, I'll tell you more about what I'll provide for you, what kind of things you'll need for the final. This sheet, a lot of times I'll just put this up on the website so you can kind of see what you'll have to work with, so you know if I'm going to give you some equations, then you'll know exactly what you're going to have to work with the day of the exam. I guess while we're at that with densities there, let's just remind ourselves of some volume formulas that you might need. What is the volume of, well, let's do the one you guys just did, of a cylinder. If you did that last homework, I think there was that one with the steel wire when we gave you density and you could use that to find the mass or something. And you had a wire that was cylindrical, so what's the volume of a cylinder? Or something close to the volume of the cylinder. Give me one correct letter that goes in there.
Like 2 pi r or something?
There's a pi in there.
I think it was pi r.
There's a pi r or something in there. Whenever you're doing volumes, you want to make sure you have cubic units here at the end.
Is it pi
So,
r squared times pi?
yeah, because you're going to have, always think about these as like you're doing the area of a cross-section here times the whole thing. So the area of a cross-section here is just a circle. You got your pi r squared for the circle times the length or the height, whatever you, if I just put an L up here, then we'll say pi r squared times the length or the height, depending on if it's sideways or standing up, whatever you want to call that. What about a box, a cube, a rectangular box or something? How do you find the volume of that? Same concept, right? If we're talking about a box and you want the volume, we're saying here, take the area of a cross-section, multiply by the height. Here, take the area of the base or a cross-section, multiply by the length or the height here. The area of a rectangle is just length times width, and then by the whole height or the length. This is just length times width times height. Sometimes I'm generous and I give you these on the exam just in case you forget, but you should know how to work with these, and you should know these formulas. What about a sphere?
4/3 pi r squared.
4/3 pi r. These all have cubic units. This is r squared times L, so that's meters cubed. This is length times width times height, meters cubed. This can't be r squared then. What does it need to be?
Cubed.
R cubed, yeah. Sure, close. Anytime we have something with a circle, a cylinder or a sphere, at least you start off by telling me there's something with a pi in there. That much we know. Yeah, and it's good to know these formulas. You'd be surprised how many engineers who've taken plenty of math and more than one physics class still can't tell me the volume of the sphere. Yeah, I know you can all look it up, I know you all have Google, but there are times where it's just useful to know some things without having to go search around for them. Plan on memorizing these. You'll use these. You'll probably have to use these two for sure on the homework. I don't remember if there was a cylinder there or not, but when we have some things that are going to be floating like a box or a ball in the water or something, you're going to need to relate the volume of those to find their densities or mass or something about the buoyancy of those in a fluid. Okay? Let's talk about pressure and depth now. And how they're related. The pressure is going to increase with depth. And the pressure is going to be the same everywhere. On a horizontal plane. You know, I've been having trouble with my writing this week, and sometimes I write words wrong or I have wrong letters, but the little layoff that we had, I came back in yesterday morning and I'm up at the board and it just feels so strange to be writing on a board again after, you know, and we had, before Thanksgiving we had tests, so I was just kind of sitting around watching you guys. I'm going to write some things wrong today, maybe for the rest of the semester, but it just sometimes feels weird to be up here after a layoff. Once I'm up here, I'm usually fine after a few weeks, but okay, so I'll show you what this means in a picture. But pressure should increase with depth. I'm just going to kind of show a fluid here. And then I'll put it in a container here. Doesn't matter. This is the line that we're talking about here, some horizontal plane where P, the pressure, is the same. Everywhere on this line, this horizontal plane is cutting through the container there. As you go further down, the pressure is going to increase with greater depth. The rho is the density of the fluid, and we're gonna apply this to fluids, we can apply this to things like the atmosphere and the air also, but this, for us, we're gonna be dealing with these in fluids here. So this density here is going to be the density of the fluid, and we're saying that as long as those two things don't change as you're going through these levels here, then everywhere on here, the pressure will be the same on that horizontal plane. We can relate two pressures to each other at two different levels from this equation here. P is equal to P naught plus rho, the density, times gravity times H, which is the depth, some distance below the surface. So this PO is the pressure at H is equal to 0. H is the depth. We're measuring from top down. This H is equal to 0 is usually at the surface, but it doesn't have to. This P here is then always the pressure that is going to be below this point right here. So on a diagram over here, if I have 2 points, one would be maybe right here and right here. If I'm saying this up here would be P naught and this would be P. Okay. This is where H is equal to 0. And this P is always the greater pressure, the one that's down below at a greater depth, which has a higher pressure. Okay. The P naught is always the one above with the lower pressure. Okay. Usually we're going to choose that point to be the surface here, but it doesn't have to be. This equation for P and P naught here can be any 2 points in a fluid here where H is the distance between them. Because your top pressure is where H is going to be 0. So your H is here. Okay. If I draw that picture again, and I just choose now, I want to take this point here to be P naught, and I want to take this point down here to be P, then my H would be measured right here. As long as your P here is the one that's at the greater depth, the higher pressure, and then the H is measured in between those 2 points, then that's what we're talking about with those 2 P's. It measures the pressure difference really at any 2 points. The lower pressure point here can be chosen to be anywhere. Okay. The reason we choose at the surface is because when it's at the surface, then if it's an open container, we can say that the P naught is the pressure of the atmosphere. Okay. So we'll know what that is many times. We can write down the pressure of the atmosphere. So let's say for this case right here, for an open container with my P naught chosen to be at the surface, P naught is equal to 1 atmosphere, and 1 atmosphere is just equal to 1.01 times 10 to the 5th pascals, or I'll just write it as newtons per square meter. Okay. This is just atmospheric pressure at sea level. And that's why it's convenient to choose that thing up here at the top, because you'll know what that P naught is. Okay. There are situations where you may not do that. Over here I just chose at random, let me just pick these 2 points. So we wanted to just choose those points there. That wouldn't be so convenient here if we didn't know what that point was. Most times you'll be able to choose it like this. On your homework, you're probably going to have one where you might have something like this, where you might have a layer of oil above the water like that, or it could be anything. In a case like this, if I asked you for the pressure down here at the bottom of the container, then I could still use this equation here to relate my pressures of two different points. I know the point up here is the atmospheric pressure. I don't know what it is down here. I might know what this H is right here. But I can't use that equation to go directly from the top here down to the bottom there. Anybody see why not?
Because your densities will be different.
Because the density is different. I can't just use this, I wouldn't know which density to use. So in a situation like this, you could go from here to here, where that would be your P naught and that would be your P. And then you could do it again from here down to here, where this could be another 2 points, and you can choose your own labeling for this with how you do it. And you would just do it twice for each location here where the density is constant. Go from here to here for one, go from here to here for another one. That's another situation here where, for this part here, where I've got it in green, with that H, that'd be a place where your P naught isn't at the top. It's just wherever you choose. And whether you call them P naught or P or P1 and P2, you know, when you choose this, you might just say, okay, let this be P1, P2, and P3, 3 different points on there, and just always let the one that's higher be the one that goes right here in the equation. The P that's solved here by itself is always the one at the greater depth. Okay? Yeah.
So after you would get that, would you just add the pressures together then? Like if it was asking for the total pressure or?
No, at that point you could just say whatever P you solve for right here, that would be the pressure at the bottom of the tank, because that's already based on a new pressure you would have found right here.
Okay.
So once you find what this one is, which would be, you know, the greater pressure here, this becomes the higher one or the lower pressure here.
So that would be PO
Yeah.
in the second. Okay, so you kind of work your way down.
Yeah. And then you don't have to add anything on, like you're not having to worry about adding on any weight from the oil or anything like that. That's all kind of built into this right here, and then you could just, that pressure, this equation relates any 2 points. And if I know the pressure at this higher level, whether it's at the surface or anywhere, as long as the density is the same in here, then I can use this. And as long as if this height here, this distance here between them was huge, and gravity actually changed from one place to the other, then this would change some, but we're not ever going to do anything like that. So G is going to be constant. We don't need to worry about that. The density for that whole container there isn't constant, but we know we can break it up and just use this for each of the 2 different parts. There's another case where the top this P naught, don't just assume that it's always equal to this right here. It is for these situations right here, which is many of the cases, but not all. Okay?